Welcome to the 2026 67th Annual SPWLA Symposium happening in Lake Conroe. It's where we're standing. We're in the poster presentation room, and we have two individuals who have worked on NMR and trying to understand T1, T2 distribution, and I'm imagining pores. You guys are trying to define the pores. Okay, we're going to jump to them. Introduce yourself, introduce the project, and then pass it to your co-author.
Thank you. So introduce myself first. So thank you very much, Troy. I am Tom Bradley. I am I'm a global, associate fellow for formation evaluation with Baker Hughes, based in Den Helder in the Netherlands. Been working in industry now for 29 years.
Whoa, right on.
And I'll hand over to my colleague, Azeem.
Okay. I am Mohammed Azeem. I, with Baker, petrophysicist. Mainly work a lot with NMR and open hole petrophysics. Been with Baker since 2013. Yeah.
Okay, my basic understanding of NMR is like a super magnet that you're dragging slowly up the hole, and it's is that essentially?
Yeah. Well, you're polarizing the hydrogen protons. You get them to line up, and then you do another experiment where you tip them over, and then how they process, the rate at what they process is where you get all the information out, right?
In fact, the way to explain it is, have you ever had an MRI scan in hospital?
MRI?
Yeah.
Yeah,
It is.
unfortunately.
Yeah. It's actually exactly the same physics, and we just apply it in oil field, as of course many people working in the industry know, to measure a lot of the formation properties we need to know. Things like porosity, permeability, in this case, also hydrocarbon saturation.
Whoa, let's get into it.
Okay, so Azeem, as you wrote most of the paper, I will actually let you take it away.
All right, so, nothing really fancy going on with this paper, except we did a good case study because we wanted to understand, the parameters that we could use for the Almelanden. Did I say that right? Almelanden chalk, okay? It's offshore Netherlands, okay? It's specifically F17 block. It's just just a little further up from Den Helder, actually.
Where I live.
Yeah. So we drilled. The operator drilled 3 wells, F17, 10, 11, and 12. So this is the formation here. We have, kind of like a plan view. And if you look at the cross section here, we have the F11, 10, and 12 is, several miles. Yeah, exactly. So it's in a little bit a different environment, except they're all within the same block and the same formation. Okay. So what we did, we looked at the NMR data and what we can figure out using cores and some formation testing data. And figure out how we can apply those cutoffs. Now the beauty is that they logged this with initially with oil-based mud filtrate or oil-based mud, and then because they had some issues with the cores and gathering cores, they logged the other 2 wells, the 11 and 12, with water-based mud. So with an oil-based mud, with an NMR, because you're only looking 2 to 4 inches into the formation, you get a lot of mixed signals with the mud filtrate, right? So the oil is going to be pretty much overlapping the actual oil from the formation, right? Or there's going to be a flushing of fluids. So is the oil that you're seeing, is that actually formation related? Is that native fluid? When you look at the T2 apparent, you would say, oh yeah, this oil that we see over here, yeah, we can just draw a cutoff line over here, which is the standard cutoff that we have is around 100 milliseconds or so. But if you look at the other wells that have been drilled with water-based mud, okay, we have those other wells where you have a completely wet, water-wet well. So you can see the resistivity, it's completely flat, really low. You have another well that is oil-saturated, but it is also drilled with the water base, and you can see the microlateral log resistivity is reading really low. So there's that's the red. So there's a quite a significant degree of flushing of the fluids. But what you do notice is that when you look at the other wells, you do notice that there's some some signal from the hydrocarbon that's actually in the T1 that you don't see in the T2 apparent, because with the wireline tool we have some gradients. We have different depth of investigation, so you use different frequencies. So you have some diffusion effect with the T2 apparent. So what happens is that lighter hydrocarbons the signal kind of compresses together, and so it's hard to draw a cutoff line. But if you look at the T1, because now we're just looking at the T2 intrinsic, we're taking away the gradient, we're taking away the diffusivity. So the signal kind of spreads out along the time scale, and so the hydrocarbon relaxes a lot further away from the water signal. So
if we look very, very closely, you can see thank you very much, Steve. You can see a very, very sort of thin line here on the T1. If you look very, very close, you can see it's actually shifting off to the left here. And that is it's very, very subtle. Again, because in this world we have a lot of invasion. So, because as he mentioned, the MX is reading basically 2 inches to 4 inches from the borehole wall. That's where your invasion is. So if you've got water coming into the formation, it's going to basically push, as you know, all that oil out from where the tool's reading, and you're going to see water. With only the oil seam that's left is the residual hydrocarbons.
So that's what residual hydrocarbon looks like, you think?
That's what we're interpreting it to be, yeah, because, yeah.
So that gives us just like a one-dimensional, okay? That gives us a one-dimensional where the T2 is with respect to what type of fluid we're looking at. But when we look at it in a two-dimensional, which is we take the diffusivity component, plot it against the T2 intrinsic, or T1, some people will call it, then you really get to see the spread of the signal and where each one of those individual fluid relaxes on the 2D NMR plot. And so what we see is the irreducible is going to be a little bit off to the relaxing a lot faster. You're going to see the movable fluid, or the movable water, is going to be relaxing, in this position time versus diffusivity position. And then you see mud filtrate, which is a very strong signal. Why? Because we have a shallow depth of investigation, right? 2 to 4 inches, quite a significant. And we have this little signal over here, which we're going to call it formation or native hydrocarbon. And why we call them this is because we see that consistently across water-based mud filtrate or water-based mud drilled wells, and you see that signal quite consistent with all 3 wells, all 3 of these. And you can only see that in 2D NMR.
Wow. You're talking about that real subtle, different blue? Is that what you're talking about?
Yeah, it's. But you see the amplitude, because it's such a strong amplitude that the reds kind of take over. It's normalized, right? So even if this is a strong signal, because this is so strong that it's gonna kind of mask. So maybe the print doesn't do quite justice on. But if you look at it closely, I have weaker eyes, but if you look at it closely, you can probably see it. So now the question, Troy, you would ask is, Azeem, and Tom, why are you drawing a cutoff line, irreducible cutoff line at around 25 milliseconds? Here's the reason why. Because when you log NMR in a water-based mud, and if you have a significant invasion of fluid and you have a lot of washouts, you're going to see a very strong signal in the irreducible. And so if we were to show a 2D NMR somewhere up here where we have quite a lot of washout, you would see a very strong signal of BVI right here. And I was like, okay, all right, that cannot be true because, well, maybe it is true. I don't know. But we need some other information to confirm that. And guess what? We had cores. And in the NMR cores, the lab did the study where they figured out the cutoff was 24.6. It's an average, but it was 24.6 milliseconds. And guess what we're using? We're using 25. So we're pretty close. Okay, so that made me confident that maybe what I'm doing is right. Traditionally, you would apply a T2 cutoff somewhere around 100 milliseconds, 92, industry standard. Wow. But in this chalk, you actually pull it back. And then you say, okay, how do you determine the cutoff between the mud filtrate and the native hydrocarbon? Well, we see the hydrocarbon pretty consistent here, so we're going to apply a cutoff right down the middle. And so that's why you see, exactly, that's why you see the line go all the way down. And that's something consistent that we see around 512 milliseconds. We see a slight subtle signal of the native hydrocarbon here, and you can also see it over here. Okay, now let's look at what the end result is. All right, so we have the F17, 10, 11, 12. This one's oil-based mud, water-based mud with water wet. And you have the water-based mud filtrate, or water-based mud with significant saturation based on the resistivity profile, right? This one's flat, so it's all flushed, and it's water wet. So when we do 2D NMRs, we also calibrate the permeability. We can get into that later, but let's look at the 2D NMR and the interpretation. Okay, so we apply those same 25 millisecond cutoff for BVI, 512 for oil in formation hydrocarbon, and this maybe the image is probably not as good when it comes out print, but this is lighter green, this is darker green. Darker is formation hydrocarbon. The lighter green, we're calling that mud filtrate or some sort of a light hydrocarbon, right? And compare that with Archie-based resistivity. Red is deep, blue is shallow, based on these curves right here. And you can see that they match up pretty well. Over here, you have a little bit separation. That's fine because there's a degree of invasion. But over here, you can see that the NMR, 2D NMR determined saturation. There is a little bit of variation, and we believe that could be noise. And if you smooth that out, and if, let's say, we average that curve out, it'll probably match up a little bit better. We plot that against the core porosity, and we get a pretty good match. We use the core permeability, calibrate, and we apply that calibration all the way across the field, and we get a pretty good consistency. Now we move over to the water and water-based mud well, and you can see, maybe you can't see, it might be a little bit difficult for the viewers, but this blue line is showing the shallow resistivity based or Archie-based shallow resistivity based Archie saturation. That's the blue, and you can see that it's pretty low, and that matches more or less within reason. It matches well with the lighter shading green. That means it's the mud filtrate, or what we're going to call it the light oil. Now, the red is going to be the deeper, and that matches pretty well with what we consider as a formation hydrocarbon. So with just these two, you can figure out that the cutoff that we're applying has, we're pretty confident in that cutoff. You go down to the oil, this has more oil saturation based on the resistivity profile, but with water-based mud filtrate, so you use a shallow resistivity Archie, and you can see that it matches pretty well. There's some spikes here and there, but that's could be noise, could be some vertical resolution, probably. Deep, that one's based on this curve right here, the deep resistivity from the lateral log, and you can see that there's quite a big delta, right? And that's the flushing of the fluids. Now, maybe some of the viewers might be asking, okay, why is there a little sliver of green? Well, it's because we have a static cutoff, right? We have a window, and so some of the signal might spill over or left to the right, so you're going to see a little bit of variation. But in the grand scheme of things, I think it applies pretty well. We have one of the SMEs from Aramco who used to be an ex-Baker, and he thinks it's pretty good. It's not so yeah, so it raises our confidence even more. It's not groundbreaking, but what it does show is that you're not completely lost if you have two different type of muds, and with just NMR, you're not completely confused when it comes to figuring out the parameters. You got to look at everything, combine it all, and figure out what the appropriate parameter is, and look at some other data, cores, and all that formation testing and sampling to really figure out what we're going to do here.
You guys did. I got a question. How important is it to have a ditch magnet while drilling before running NMR?
Okay, in my experience, I would run it every time. Every time. Even with the tool, when you're logging wireline, run it every time. Get that metal shaving out, because it's better safe than sorry. Now, unless if you have, if you don't have the magnet on the shop or whatever, that's a different story. But from my experience, whenever I do a report and I say, hey, engineer, log it this way, I always make sure I put it in an email, bold text, use magnets, because you can't really depend on. Sometimes the hole's not in the right condition. Maybe they haven't circulated the mud. You never know, right? So it's better safe than sorry.
Yes, sir. Thank you so much for presenting, man. Thank you for being here. Thank you, guys.